Do I start now, David? You will tell me when to start.
Yes. Okay, we are recording, and I want to welcome everybody. I apologize. We've done quite a few of these. I don't even know how many now, 50 or 60 of these. They go pretty well, but I had some computer programming changes this week, and because of that we had a few glitches in our email system and our time zones for these with people all around the world. I realized that when if I get the time zone times wrong on these events, that in fact it does affect how things go. So I do apologize. That's I think I have fixed those problems. But regardless, what's good about this whole system, we do have, as we say in the industry, the software industry, a backup, and that is this entire thing is recorded. So if you can't stay for the entire time, you can go back to our database and in fact see Tolga's entire talk in its entirety with audio and all the slides, and we do record now we even have a transcript of the chat. So we're very happy and pleased to have Tolga here today. He is coming to us live from Istanbul, Turkey. And it's one of the amazing things about this. And he's going to be talking about Einstein's non-conform analogy between rotational and gravitation, rotation and gravitation, a critical analysis. And we're really happy to have him here. And without any further ado, I'm going to disappear here, Tolga. And when you get close to the end, I should reappear, and we'll then be able to take questions. But we thank you very much for taking the time with being here with us. And the floor is yours. You can start. Thank you so much.
Thank you so much, dear David. Once again, I'd like to welcome everyone who has joined us. It's a pleasure to be with you. I'd like, first of all, to thank Dr. David de Hilster for having, according to us, to me, to myself, and in fact to the entire science community, such a striking opportunity. And I like to also thank to few people, if you allow me only a few seconds, chiefly to my co-authors, my dear friends, Professor Arik and Professor Kholmetskii. Professor Arik is from Istanbul, Boğaziçi University, and Professor Kholmetskii, I'm sure he's following us from Minsk. He's now in Belarus. I like to thank to Peter Rollins, to Vladimir and Tatiana Gradishev, Professor Rozanov, Professor Alvin van der Merwe for his sageness, Professor Vezirol, Professor Oktay Sinanoğlu, Professor Marshall, the research director of French NASA, the ONERA institution. ONERA is for Organisation Nationale d'Études et de Recherche Aérospatiale. So you can see my French is not bad either at all. And I like to thank to Professor Ude, to Professor De Haas from Holland, Dutch land, who is with us right now, to Professor Love from California, and to many other people I like to talk to, I like to thank to, and I like to ask them to forgive me if I couldn't pronounce their names. So this exciting, for me, exciting topic is something I'm thinking about since about my doctorate period of time I spent at MIT. Since then, the beginning of 1970s. And here's my book, my own, The Meaning of Relativity, Einstein's book. In fact, the copy I had, I'm sure most of you have it as well. And I like to take you to page 60 of this book with a little drawing of mine. Here it is. So Einstein's approach is as follows. So he considers a rotating disk over here, as you see, and he proposes to establish an analogy between the rotating disk and the gravitational world. In fact, he considers what happens to an object sitting at the edge of this disk, moving with a tangential velocity v. But before seeing how he considers this problem, let's go to the peculiarities of this problem. It's a monumental analogy, of course, but of course the idea is to bridge the gravitation with acceleration, or the effect of gravitation with the effect of acceleration. So then let's try to enter Einstein's brain and try to reformulate the problem. So we have a spinning disk, and we have the feeling that acceleration works as gravitation, or vice versa. So we have a celestial body over here of mass capital M, and we have the same object M right over here at a given distance from the center of the gravitational body. So the object is affected by the gravitational mass over here. So the effect-free location in this picture, the gravitational world, which I will call, is infinity. Then the effectless location in the accelerational world, which we can call the disk world, is the center of the disk, in fact. So the center of the disk is the location where, if the object did sit at, would feel absolutely no effect of gravitation, because there is no gravitation at the center. And let's now take a look at what is the most influential location in the gravitational world. So still assuming that the object is influenced by gravitation. So the surface is the location which is much more influential, obviously, than any other place between this point and infinity. And if we go even further in the inside of the body, and then we can feel that the object would be even more influenced. And the most influential location for the gravitational world is the center of the celestial body. Now, which location is the most influential location for the disk world? It is the edge of the rotating disk, and that should be, with respect to this analogy, no further point beyond the edge. So, in fact, the gravitational world is a closed world, and the disk world must also be a closed world. And in order to be able to bridge this world, the disk world, to the gravitational world, we have over here in the disk world consider just the same way a closed world, and there should be no exterior space of this closed world. But very unfortunately, Einstein has taken a look at this picture from the outside. There is no outside of this world. I mean, you can of course take a look at what happens to the object rotating with a given speed from the outside. But if you like to bridge gravitation and acceleration, or the accelerational world and the gravitational world, then you have to close the disk world, and you have to take a look at the world, what happens to the object from the center of this rotating disk, rotating with same angular velocity as that of the disk. If, on the other hand, you indeed take a look at rest to the gravitational world from infinity. So the starting point already of bridging the gravitational world and the accelerational world, unfortunately, seems to delineate an unconformed analogy. Now, if you think that indeed the object sitting at the edge of the spinning disk undergoes an effect, which is similar to the gravitational effect, then looking at this object at the center, being sitting at the center of the disk and rotating with the same angular velocity of that of the disk, you should already accept that, accepting the similarity between the effect of gravitation and the effect of acceleration, the object at the edge of the disk should undergo a given effect. However, now I'm going to take you to the page 60 of Einstein's book, The Meaning of Relativity. I hope it's going to appear. I just pushed the button. I clicked it. And it doesn't come out. Let me try again. Okay, here we have. Okay. So, okay, no, that's fine. So, here, before I present for you the page 60 of Einstein's book, here we have, in fact, a conform analogy between the gravitational world and the disk world. The edge of the world of concern, of the gravitational world, must be the center of the celestial body, whereas the edge of the disk world is the edge of the disk, where the object would feel the highest effect of the acceleration. The effect-free location of the gravitational world is infinity, and the effect-free world of the disk world is the center of the disk. So, not setting up things the way this small table evokes would necessarily introduce a non-conform analogy, and which is unfortunately the case. Now, here is page 60 of Einstein's book, and here there is an intriguing footnote. Einstein had given a thought, in fact, to what I'm talking about, and he made a footnote on page 60 of his book, which made one last print right before he died. And here is the footnote. I'm making it clear for you. He says, Einstein says on the footnote on the bottom of page 60 of his book, The Meaning of Relativity, these considerations assume that the behavior of rods and clocks depends only upon velocities and not upon accelerations. He hoped to have such an occurrence. But this is already in contradiction with his principle of equivalence bridging acceleration and gravitation, because someone sitting inside of the rotating disk, according to his principle of equivalence, should not feel the difference between acceleration and gravitation. So then someone, an observer sitting at the center of the spinning disk and spinning with the object with the same angular velocity as that of the spinning object, meaning at rest with regards to the object, would be able to tell that the object is undergoing either acceleration or gravitation, if there is indeed a one-to-one correspondence between the two effects, occurrences. So already within its framework, this statement, unfortunately, is not consistent. But what he says, leaving aside whether this is consistent or not, what Einstein says is that the observer sitting at the center of the disk and spinning, bearing the same angular velocity as that of the object, but being at the free, location-free situation, would not detect any difference on the object, since he is already at rest with regards to the object, and Einstein assumes that the behavior of rods and clocks depends only upon velocities and not upon acceleration. So the observer at rest at the center of the disk, at rest with regards to the spinning object, he's not moving with not moving, or the object is not moving according to this observer, and then he is not to feel any difference that the object would undergo. So in fact, that's the whole contradiction I'm going to talk about now, and I'm going to analyze, unfortunately. But let's summarize what I'm at right now. I'm saying that Einstein has not considered the influence of acceleration as such, I mean as acceleration only, but instead reduced the effect of acceleration to the mere effect of the instantaneous velocity, looking at things from the outside of the spinning object. This is already a non-conform analogy. So the velocity, the instantaneous velocity, is picked up at the given time, and Einstein treated this effect as a tangential displacement effect, leading to the usual Lorentz time dilation for periods of time and Lorentz contraction for lengths, though only lying along the direction of motion, and finally has drawn his analogy between the effect of acceleration and the effect of gravitation to come out with a new theory of gravitation. The intuition is deep, it's fantastic, but unfortunately the analogy, the way it has been set, is a non-conform analogy, and it is to lead to unfortunate contradictions that I'm going to detail just a little bit. Now, okay, so he has, in fact, a continuation of his statement on page 60 of his book. It says, or at least that the influence of acceleration does not counteract that of velocity. But this is just a cautionary statement. He ultimately had not used this statement, the continuation of his statement that I just referred to. So this is just a dummy statement. So to our understanding, Einstein's consideration of the effect of acceleration unfortunately blocked him fatally, also blocked the science world for almost a century. Now, what would happen if we now consider the analogy the way which he should have said, and the way other people throughout perhaps 100 years by now may have said. So I'm going to detail this a little bit, but let me just give you my conclusions, our conclusions in fact. So according to Einstein's standpoint, the spinning disk is seen, just this last row over here on this table shows. So it's classically seen from the outside world, where Einstein sits, but unfortunately leading to the non-conform analogy that I just referred to. So his mass must dilate as induced by the usual Lorentz transformation. His length alone, just the displacement, the tangential displacement, the rods, or the length of the object must contract. And his period of time, I mean the period of time that this object would display. So if this is a clock, this is the unit period of time. So that period of time must get stretched again as much as the Lorentz factor coming into play. So this is just the Lorentz time dilation. However, as I'm going to detail pretty soon, for our clock sitting at the edge, an atomic clock, a nuclear clock, anyway, any object, as I'm going to talk about pretty soon, must embody an internal dynamics. So that internal dynamics should correspond to a given rest mass. That rest mass, because of the energy that one has to furnish to the object in order to remove it from the field and bring it to the location-free point, which is the center. So the rest mass of the object with regards to the observer at rest with respect to the object must get decreased. I'm going to explain this to you pretty soon. And the size of the object shall get stretched in every direction, not only the direction of the displacement, and the period of time, devilishly, we are going to find out, up to a third order time expansion gets stretched exactly, or almost exactly, by the same amount. So this is devilish, I find, really. So let's get to the next slide. So Einstein's considerations of the general theory of relativity lied on length contraction and period of time stretching, as observed non-conformally from the outside of the disk. And instead of both length and period of time stretchings, by an observer rotating with the same angular velocity as that of the disk and situated at the center of the disk. So the way we conceive things, Einstein unfortunately has picked up an invalid kernel. His length, then the length contraction and period of time stretching in building the general theory of relativity, whereas we believe he should have picked up the length and period of time stretchings, as it will become soon, pretty clear pretty soon, I hope. Okay, now here's our next slide. Okay, now I hold the privilege of having derived the gravitational equation of motion, in fact, very easily, frighteningly easily, through just the law of energy conservation and quantum mechanics. And I'm going to sketch the idea in few words. So this approach lies within the frame of the law of energy conservation. Quantum mechanics too, obviously. And I'm going to show that even the Broglie relationship, which is the other pillar of quantum mechanics, can also be derived from the relativistic law of energy conservation. So in such an approach, the relativistic rest mass must already be altered by the acceleration of the field. So let's go back to the gravitational world. So we have the celestial mass, capital M over here. The object's rest mass at the altitude r, as measured from the center and as assessed by a distant observer, is m of r, and the distance between the object and the center of the body, the celestial body, is r. So in fact, this is nothing but the Newton gravitational attraction law, but only for us valid if the two bodies are at rest with regards to each other. So if now we move that object of mass, rest mass, m of r, from r to r plus dr, then based on the relativistic law of energy conservation, we must pile up that energy into the object's body itself. So its rest mass must get increased as much as dm of r. So this is the energy, if I multiply by this by c squared, that's the energy furnished by us to the object to move it from r to r plus dr. So the integration of this simple differential equation leads to this rest mass expression. So the rest mass in the gravitational field, according to us, must be decreased as this expression shows. So this is the m sub 0 infinity is the rest mass of the object at infinity. As if we multiply by c squared, that's the internal relativistic rest energy, I like to attract your attention to the fact that general theory of relativity considers the increase of rest masses, in fact, because of the ill-set analogy in the gravitational field. However, the energy should be decreased. Here, the energy, the rest energy, along with the rest mass, is decreased in the gravitational field. This is nothing else but the gravitational redshift, meaning the lights. Any light coming from the object, this may be an hydrogen atom, for instance, sitting on the surface of the sun. So the lights coming from the sun, already measured as assessed by a distant observer, but as referred to the surface of the sun, must get decreased, meaning the lights should be redshifted. Okay, now, not further that, this is important. We have not borrowed the Newton's attraction law plainly from Newton. I was able to show that, and I hope you are going to find this very interesting, that the 1 over r squared dependency of Newton's force, and only for masses at rest with regards to each other, can be directly derived from the frame of the special theory of relativity. I mean, if you consider just a dipole of masses, two masses at rest with each other, and you move that dipole with a uniform translational velocity, and you set the force in between these two masses as the special dependency of these, the force between these two masses is 1 divided by r to the power of n, then the special theory of relativity makes that the power n must be identical to 2. Okay, so whereas Einstein's redshift, the gravitational theory's redshift, is given by this expression. So this is only the energy, not the rest mass. So the energy is decreased by this expression. So we have over here a singularity, as most of you know about. But the point I like to get to is that this expression comes to be the same as the expression I just have shown to you, up to a third order of tidal expansion. Okay, now I will tell you in a few words how we can set up our gravitational equation of motion. And this is very easy, and we have detailed this with Professor Gerrit Sobzik, whom I adore, along with my other colleagues. I'm terribly happy to see that he's around. So here is the idea. Now, suppose we have a planet rotating around the sun. Now, we can simply assume that the motion is made of two steps. First of all, you move the planet from infinity to a given location on the orbit. So, and then on this location, you deliver to the planet its rotation, rotation or motion on the orbit at the given location. So, now for the first step, the operation of moving the planet from infinity to the given location quasi-statically must decrease its rest mass. We can understand this as follows, if you like. We pick up the planet at the given location and move it to infinity. Then you have to deliver to the planet a certain amount of energy, and that energy, because the sun doesn't move, because it's extremely infinitely, can be assumed infinitely heavier than the object in question, then the object is to pile up the energy delivered to separate it from the sun. So if you now conversely move the planet from infinity to the given location, then its rest mass ought to get decreased. So now to deliver as the second step its motion around the planet from the given location on, then you multiply the rest energy by the Lorentz transformation factor, 1 over square root of 1 minus v squared divided by c squared. So for a closed system, this is the overall relativistic energy. It ought to be a constant. That's in fact nothing else but the integral form of our equation of motion, gravitational motion. And if you differentiate this with respect, if you take the total differential of this expression, since the right-hand side is a constant, it should turn out to be 0, and then you'll end up with the differential equation of motion of the planet around the sun. You can right away check that this comes to be the same equation, the same gravitational equation of motion as the one written by Newton. Now, what is the expression led by the general theory of relativity? After cumbersome setups and mathematical operations, the equation, a similar equation of motion can be written as follows. So that's the overall relativistic energy, and not the rest mass. The rest mass varies differently in the general theory of relativity. So that's the rest mass changed due to the curvature of space or geometry, and divided by square root of 1 minus v squared divided by c squared, and that's a constant. So it's already striking that these two expressions are the same up to a third order of tidal expansion, except that we have arrived to my equation of motion in only few lines. This is scandalous. I can admit that. And not that, whereas we have over here a singularity for the general theory of relativity, we have in our expression of gravitational motion, or that's the integral form, in fact, of the equation of gravitational motion, we have no singularity whatsoever. Now let me proceed a little bit further. Now, I'm going to apply the same idea to the disk world. So we go back to to page 60 of Einstein's book, The Meaning of Relativity, to the Gedanken experiment he has considered. So we are going to solve his problem our way. In fact, I'd like to thank Professor Marshall, the General Research Director of French NASA, who had considered very seriously for a great period of time in order to be able to detect the difference between the end results of the general theory of relativity and our end results. But unfortunately, the precision of his instruments fell too short, and he invited me to think of an experiment where we can, or one can, measure the difference between the two theories. In fact, I came up with Einstein's own Gedanken experiment, but we are going to handle it now our way. So anyway, only experiments could have made manifest which approach is closer to reality. In fact, Einstein's own Gedanken experiment turned out to be the basis of such a comparison, because as we will see, on that basis, the difference between the two approaches become quite larger and detectable. Okay, so I go back to Einstein's spinning disk Gedanken experiment. However, as an observer, we propose to sit at the center of the disk. That's the location. That's the location which is free of any effect. And not only that, we propose that, again, on any radial direction, in fact, the observer is at rest with regards to that radial direction when the disk spins. So, as viewed from the outside, the observer at the center of the disk shall rotate with the same angular velocity as that of the spinning object. So that's that observer observe another observer, if you like, moving quasi-statically the object from the center of the disk toward the edge, or vice versa, moving the object quasi-statically, this is important, from the edge toward the center. So what will that observer sitting at the center of the disk will see? He will see that the force experienced due to the centrifugal the rotation phenomenon the disk displays, but he doesn't have to say anything. He doesn't have to know anything about the rotation of the disk. He will note that the force the object is subject to is proportional to the distance on which the object resides. So we know that constant, that constancy is nothing else but the square of the angular velocity of the disk, of the spinning disk. So if we move now that object sitting at r as much as dr, that's the energy we have to furnish to it, not preventing it from falling toward the accelerational field, or vice versa. We can think we move the object from the edge or from the distance r as much as dr backward. So then we have to the object must pile up that energy, or if we move the object from r to r plus dr, the object's rest mass must get decreased just as much. So this is due to the relativity law of energy conservation. That's a closed world. Energy must be conserved in any frame of reference. In that this world, it must be conserved as well. Although it's not a Lorentz invariant quantity, energy must be conserved anyway. So then the observer sitting at the center of the disk must come to the conclusion that the object's rest mass or rest energy is decreased as the object moves quasi-statically toward the edge. Okay, now that's simple. We can integrate this just the way we integrated the similar equation written for the gravitational world, and we see that the object's rest energy is decreased as it is moved quasi-statically from the center toward the edge. Okay, so this can be written as this expression shows over here. So the rest energy of the object at the location r from the center of the disk is equal to its rest energy at the center of the disk times 1 minus its binding energy divided by its rest energy. So I call this the static binding energy the object develops in the centrifugal field. In fact, in any field, that's the beauty, the object interacts with. So we are not only bound to the centrifugal field at all, neither to the gravitational field at all. In any field the object interacts with, we have such an expression. Thus, within our approach, already in the closed disk world, the rest mass, or better, the rest relativistic energy, must get decreased due to the centrifugal acceleration. We expect accordingly a slowing down of the internal mechanism of the object. Why? Because the internal rest relativistic energy decreases, means its internal energy decreases, meaning its internal dynamics gets weakened. So any phenomenon associated with that, any phenomenon associated with that should be slowed down. So the period of time associated with that phenomenon, with the internal dynamics, should be stretched as much. So I will come back to this in a moment. I have not. Well, we assumed in the foregoing derivation that the disk is much too heavy as compared to the object, so that we don't have to consider the angular momentum conservation. But we have handled that problem to no problem. Apparently, Ozan tells me Harry Ricker asks me a question. Did he say the rest energy is yes, I said the rest energy is decreased. Yes, indeed. The rest mass, or the rest relativistic energy is decreased if the object is moved from the center toward the edge of the disk. Now, we are in the disk world. If we take a look at things from the outside, we can well do that too. Being cautious that we are not going to establish an analogy between the gravitational world and the disk world, just looking the spinning disk from the outside. But then another effect, which is that of Lorentz dilation, comes into play. That's in fact, we have two effects when we take a look at things from the outside. First of all, the effect of acceleration with respect to an observer rotating with the same angular velocity as that of the disk and observing the object from the center, and as a further effect as seen from the outside, which is that of the displacement, the one in fact essentially pinned down by Einstein himself. So Einstein had considered that latter effect, the effect of displacement, but not the one specifically due to the centrifugal acceleration states. Too bad, but that things are the way they are. Okay, now here I summarize some easy theorems, and I'm going to generalize these theorems pretty soon. You may like to take them as postulates if you do not assume the energy conservation law, but in fact, if we assume the relativistic energy conservation law, then these are facts that I call theorems. So the energy conservation law, in the broader sense, drawn by the relativistic equivalence between mass and energy, requires that the rest mass of a particle, when embedded in a field the particle interacts with, in every respect, decreases as much as the binding energy coming into play. In fact, nuclear scientists are well acquainted with that. This is something I knew when I was a PhD student at MIT, and I applied either in my nuclear physics problems or in my nuclear engineering problems pretty often, and we all did teach this throughout our courses. Okay, so this is nothing else but the relativistic law of energy conservation is equal to mc squared. So any energy has got a mass counterpart. So now this is internal dynamics is an expression I wanted to introduce to the scientific world. So any entity, in fact, has got an internal dynamics, and our theorem too says that any internal dynamics the particle may embody along with a given mass, m sub 0 infinity, which we call clock mass. I like to call this a clock mass. It works as a clock mass if the internal dynamics works as a clock. So the clock mass interacting with the field of concern in its entirety must accordingly slow down. Why? Because its internal dynamics gets weakened as much as the binding energy coming into question, into play. Thus, the frequency associated with that internal phenomenon is redshifted as much as this expression, where E sub B is the binding energy coming into play. And I'm going to present to you these theorems, nothing else but outcomes, findings which can be achieved on simple quantum mechanics. So this result is the same as the redshift predicted by the general theory of relativity, where the particle embedded in a gravitational field, though it is obtained through a totally different setup than that of the general theory of relativity. So the corresponding period of time is accordingly stretched as much as the binding energy coming into play. The present approach furnishes the end results of the general theory of relativity through, though, a totally different and much too simpler setup. So a concurrent theorem 3 will tell us that concurrently to the decrease of mass, of rest mass, and the stretching unit of the unit of period of time, the clock space size, the clock motion takes place in stretches as much. In fact, it's nothing else but h nu is equal to m sub 0 c square. If the rest mass decreases, then the total energy to be associated with that energy, that rest mass is decreased. The frequency taking place next to the Planck constant h nu, when you write, it should be decreased as much, then the period of time stretches just as much. And if the frequency stretches, the frequency diminishes, decreases as much, then the wavelength to be associated with it should stretch as much, which is the size stretching, nothing else I'm talking about. Okay, so here is a Yarman theorem. So I'm going to, so I hold honor to have been able to derive all the previous results, generally based on quantum mechanics. We have a quantum mechanical setup of the object of concern. So suppose we have the hydrogen atom sitting on the surface of the sun. So we have either the relativistic or the non-relativistic description, quantum mechanical description of that hydrogen atom. So, okay, so the general quantum mechanical theorem I'm talking about tells that a relativistic or within the framework of the relativistic or non-relativistic quantum mechanical description of the given object, depending on whichever may be appropriate, even then within the framework of the Schrödinger equation, this description points to an internal dynamics. For instance, for the hydrogen atom, you may like to consider for the simplest case the electron rotating around the proton, or you don't have to, but it is a question of an internal dynamics anyhow. It's a question of a total energy, which shall come out as the eigenvalue of the quantum mechanical description. So this description points to an internal dynamics which consists in a clock motion achieved in a clock space along with a unit period of time. That description excludes any synthetic potential energies which may otherwise lead to incompatibilities within the special theory of relativity. With the special theory of relativity, it is supposed to be based on K particles. For the case of the hydrogen atom, there are two particles, the electron and the proton, altogether. If then different masses involved by this description of the object at rest are all multiplied by an arbitrary number gamma, then we have the following two general conjoint results. Here they are. The total energy, which I call E sub 0, associated with the given clock's motion of the object is increased as much, which can be understood quite easily, because if you multiplied the rest masses by a given number, then the total energy to be associated with that setup shall indeed be increased as much. This is something the special theory of relativity would evoke anyhow. Or the same, the unit period of time of the motion associated with this energy is decreased as much. This is a quantum mechanical result. And something perhaps less obvious or less trivial, the characteristic length or the size, R sub 0 I called, to be associated with the given clock's motion. Suppose this is the hydrogen atom, then that size becomes the average size of the hydrogen atom, even quantum mechanically speaking. So that size to be associated with the given clock's motion of concern contracts as much. So we have, you multiply within the frame of the quantum mechanical description of the object you have at hand, all the rest masses by the same number, say gamma, then the total energy is multiplied by gamma. The period of time that the internal dynamics you visualize is diminished or decreased by gamma, and the size of the object is decreased by the same. Ozan, I lost the screen. Okay, it's here. Okay, no problem. Okay, no problem. So what is important here is versus what Einstein conjectured at the beginning is that mass and energy, first of all, do vary in the same direction. Also, speeds of time and sizes do also vary in the same direction. So mass increases, energy increases, the period of time and the size contract, or vice versa. If the rest mass in question is decreased, then the energy is decreased, obviously, but this is not the situation for the general theory of relativity. And conjointly, the period of time, also the internal size of the object, are stretched by the same factor. So that's my quantum mechanical theorem. Now, this quantum mechanical theorem, in fact, displays a very interesting matter architecture. I mean, we all know that E times m sub 0, I mean, the energy times mass, the clock mass I call, the space, the size, the square of the space size also ought to be proportional to h squared. But, in fact, what I come to is that over here, this quantity over here, E energy times mass, or the clock energy times clock mass times square of the clock size, is an invariant with respect to any mass change in the quantum mechanical description of the object. Of course, assuming that all masses are altered by the same coefficient. So, because, I mean, that's quantity over here occurs to be as well Lorentz invariant if the object altogether moved in a uniform translational motion. So, these two occur together. I mean, the invariance of this quantity, energy times clock mass times square of the clock size, versus to any change in the rest masses in the description of the object. So that's an invariant, as I have shown. It is also a Lorentz invariant if the object in its entirety is moved throughout the uniform translational motion. So it says that, in fact, any object cannot be structured in just a random way. Energy and clock mass and clock energy and the space size ought to be architectured in just a way, in such a way that if the object is moved, the end results of the special theory of relativity hold, or vice versa, because the end results of the special theory of relativity hold, then the object must be structured in just a given way. It's the same for with respect to the gravitational field or any field, in fact, the object interacts with. So, because we have the end results of the general theory of relativity, and you have to be careful that I mean the end results of the general theory of relativity and not the general theory of relativity itself. So, in order to have the end results of the general theory of relativity, then the object must be structured in just a given way, or vice versa, because it is structured in that way, then we have the end results of the general theory of relativity, or in fact, the end results, the object in question would display in any field it would interact with. I call this occurrence the universal matter architecture, and in fact, here is an example, which is not a trivial example at all, that I had established some time ago. In fact, I established a whole new systematic of diatomic molecules. I was puzzled and I found it something very enthusiastic. In fact, so I thought of diatomic molecules. So a diatomic molecule consists of two atoms, and these atoms do vibrate, which we call the vibrational phenomenon. So the molecule is structured in a given space size, which can be measured by the length, the distance in between the two nuclei coming into question, and there is a vibrational period. So there are three, in fact, basic quantities, essential quantities that we can associate with the atomic molecule. It is the clock mass. Here it turns out to be the reduced mass of the atomic nuclei, the period of time, which is the vibration period of time, and the space size, which is the internuclear distance. So here in the ordinate we have y-axis, we have this vibrational period of time, and here we have a quantity in terms of the clock mass and the square of the size, internuclear distance. And look how beautifully the diatomic molecules are structured. Here we have the hydrogen atom, lithium, sodium, I'm sorry, lithium molecule, I meant lithium, sodium molecule, sodium, potassium molecule, and so forth. All the alkali molecules. Why I have chosen alkali molecules? You can choose, in fact, any set of molecules belonging to a given chemical family. Why then? Because these molecules do bear the same electronic properties, one may conjecture. So the slope of this straight line, in fact, tells you about the electronic property of the bond in question, occurring just in the same way for all molecules of concern. So matter is structured in just a given way. Because matter is structured in that way, then if, say, a sodium molecule is brought to a uniform translational motion, then we have the end results of the general theory, of the special theory of relativity, meaning that because mass shall be dilated by the relative energy coming into account, then its size should get contracted as much, and so forth. And the same holds for the general theory of relativity, our way, of course. Okay, now I go back. I told you all that just to tell you how the internal dynamics of the spinning object put to the edge of the rotating disk right at the beginning will be affected by the rotation. So the object, say this is a nuclear clock or an atomic clock. We have picked a nuclear clock. I'm going to come to details pretty soon. That nuclear clock has got an internal dynamics. So this is this clock is affected by the centrifugal field. As seen from the outside, it is also affected. It must be also affected by the Lorentz tangential displacement. So the period of time, its internal period of time, say t sub 0, must be stretched by the factor we had just pinned down when we saw how the rest mass is decreased as you move the object from the center of the disk toward the edge. And now we know, according to our quantum mechanical theorem, that if the rest mass is decreased by a certain amount, then the internal period to be associated with the internal dynamics of the object shall be stretched as much. So the period of time t sub 0 is stretched by that amount, just due to the centrifugal acceleration. And then, but besides that, due to the displacement, that period of time is furthermore stretched by the Lorentz factor. So that what we expect is that the period of time approximately becomes t sub 0 times 1 minus, this should be plus, 1 plus omega square r square, or v square divided by c square. So that period of time is stretched twice, relatively speaking, as well as predicted by Einstein. Here too, the sign should be plus and not minus. I'm sorry for the mistake. Okay, so I'm skipping this slide because it takes care. It takes into account the angular momentum conservation law. Then the expression for the rest mass decrease shouldn't be exponential, but it should be governed by this form over here. So I'm going to come to it anyway. So someone is telling me something. Ozan tells me. Who? Ozan who? Harry Ricker. Okay. Harry tells me that this point was not clear in the presentation. I thought it's confusing. Now we can. Okay. What's confusing? Okay. Let me repeat then this point. Okay. What I'm saying is okay. What I'm saying is this, Harry. Okay. So here we have. Now when you take a look at the object from the outside, the spinning object from the outside, what I'm saying is that, of course, we have to measure Einstein's effect, which constituted the basis of his analogy between gravitation and acceleration. But besides that, contrary to what he hoped, the object is under a centrifugal field, and according to an observer who is at rest with respect to the spinning object, meaning spinning with the same angular velocity as that of the object, already the object is in the centrifugal field, and the object must experience an influence due to the field. And already the observer at the center must measure a redshift. If light is issued from the object, then the observer at the center must measure a redshift. According to the outside observer, that effect holds, and next to this effect, Einstein's effect 2 holds. So the two effects superimpose. So that's what I'm saying. So, in fact, the time measurement, the time dilation factor should be more enhanced than the plain Lorentz time dilation effect. In fact, as you see, we have over here just 1, and over here 1 over 2. And again, I correct the sign over here. It should be plus. So the time is stretched. So Harry Ricker says something. You are saying the rest mass increases as the acceleration increases as it moves away from center. Okay, I'm replying to Harry's question. He said, what I'm saying is that the rest mass, when you move the object from the center of the disk toward the edge, must get decreased. And this is a requirement imposed by the relativistic law of energy conservation. Vice versa, if you move the object from the edge of the disk toward the center, then its rest mass, as observed by the observer sitting at the center of the disk and spinning with the same angular velocity as that of the disk, must get increased as much as the energy you furnish to it in order to remove it from the field. Okay, so Harry says, I got the idea all right. Thank you very much, Harry, for the question and for the interruption. And I thank Ozan, who just attracted my attention. Dear Gerrit says something. Maybe a better example is the example of water generating electricity in the hydroelectric power. Yes, indeed. So when a water drop falls from a high altitude, then when it is stopped lower on the valley, then its rest mass, according to our approach, should get decreased. This is as much as the energy you have to refurnish to that drop in order to move it upward back to the dam. Thank you very much, dear Gerrit. Okay, so here I continue. Okay, now here are the results of the experiments performed by my dear colleague, Professor Alexander Kholmetskii, and his colleagues back in Minsk. So we are considering the Einstein's Gedanken experiment. In fact, okay, so we put at the edge, Alexander and Sasha and his team took a cobalt source of cobalt isotope 57 and an iron absorber isotope 57 at the edge. So we are talking about the spinning disk of Einstein. So the cobalt source emits gamma rays, and those gamma rays are absorbed. Some of those gamma rays are absorbed by the iron 57 isotope. So let's talk about a nuclear clock, in fact, in short, not to mess up things much. So we are talking about a nuclear clock sitting at the edge of the spinning disk, and we have a detector outside, and it detects how many gammas are not absorbed. So what does rotation does, in fact, to the nuclear clock is, so we have over here a Mössbauer, this is a resonant valley, in fact, nothing else but a resonant valley. That resonant valley of the nuclear absorption, we are talking of the nuclear absorption of a given energy or gamma ray. So normally that valley is shifted due to the both rotation and centrifugal influence. So here we have the count rates. Here we have the number of revolutions of the spinning disk. So we have 120 revolutions. Here we have 110 revolutions per second. So according to Einstein, there is only the effect of the displacement. And here is what would Einstein's general theory of relativity's basis predict. So that's the valley of the resonant absorber, so it should go upward. Because we have two effects superimposing with each other, our valley, the resonant valley, occurs at much lower velocity. So in fact, what we expect is that our effect should be twice, relatively speaking. I mean, the shifting must be twice as that predicted by Einstein's displacement effect, and that's again the basis of the general theory of relativity. That's the basis. That's the root of the principle of equivalence of Einstein. The way he did set up, in fact. So what we observe is that our resonant valley occurs is at 90 revolutions per second. So these are data. And this is in fact our prediction of how the energy would shift for the resonant valley. And the minimum, I mean, just focus on the minima here and here. Here there is another minima. It goes upward. So our minimum occurs at 90 revolutions per second, and Einstein's minimum occurs at 100 and something revolutions per second. And as you see, the square of 126 something divided by 2 is equal to the square of R minimum. And in fact, this is the data which comes to match very satisfactorily with our prediction. Of course, at high velocities, we have a little divergence. We could not understand yet where this divergence comes from. And we are about to repeat the experiment with other isotopes, most likely, and see perhaps in a clearer way what really occurs. But these results already, I think, are sufficient to put at stake the basis of the general theory of relativity, meaning the principle of equivalence, the way it had been set. So in fact, we long ago that Alexander Sasha and his team had performed this experiment in Minsk about a year and a half ago. We had pinned down that the experiment, that Gedanken experiment, was in fact achieved by Kundik. In 1963, he published his results. I like to tell you a story about it. I told Sasha that I couldn't find in the literature any results with regards to such an experiment. And I said I was a little surprised. I said to Sasha, please look for yourself and let me know about the results. So we were in Moscow. We had presented with Professor Metin Arik and Professor Ozan our predictions about such an experiment in 2007 in Moscow, and where Sasha got very much interested in performing the experiment. Then Sasha went back to Minsk, and he wrote to me. He said, "Well, Tolga, we pinned down the experiment, and unfortunately, I have to let you know that within 1% of precision, Kundik reports that Einstein's prediction is correct. I'm sorry for your prediction," he said. And I said, immediately afterwards, I received this message, "Sasha, please send me the article. I'm practically sure that there must be a bug in it." Before I received the article from Sasha, Sasha wrote to me back. He says, "Well, Professor Yarman, we have already detected an error of 20% in the processing of data, meaning that data, unfortunately, was distorted, or an error occurred in the data processing. We wanted to publish this mistake where the original paper by Kundik was published. We had quite a difficult struggle with the editor and with the referees. One of the referees said, "Well, the fact that this paper had been cited quite a few times only throughout very many decades must show that our audience is kind of conscious about the error in question." Well, that was the referee's standpoint. We were fortunate that Physica Scripta, the Royal Swedish Academy's physics review, was brave enough to publish our results. So we were already ahead, having pinned down the error, at least perhaps committed throughout the data processing by Kundik, and having already published our results. So here are results, and we believe that these results already are satisfactory to put at stake, as I said, the conception of the last century. This is very bad, very unfortunate. I like to confess that I have to state that I love to state that I admire Einstein. I was brought up by his results. This is nothing against the Grand Master's conception. Any one of us can do mistakes. Some people, unfortunately, get it personally. When I say that the general theory of relativity is, unfortunately, had started out erroneously. In fact, what we did over here up to this point with my colleagues, Professor Sobzik, Gerrit Sobzik, Professor Kholmetskii, Professor Mitsevich, Professor Arik, Professor Ozanov, what we did was nothing else but to apply the relativistic of energy conservation, and we owe, in fact, the special theory of relativity all by itself to the Grand Master. So Ozan warns me that there is another question over here. Tolga, where does the factor 2 come? Okay, great, Thomas. The factor 2 approximately comes from the fact that thank you for the question. The effect of acceleration as regards to the observer spinning with the same angular velocity as that of the object at the center of the disk. So the effect caused by the centrifugal force all by itself is equivalent for small velocities to the Lorentz time dilation effect. So Einstein had not considered the effect of acceleration. He says only velocities matter and not acceleration. So, according to him, the observer sitting at the center and moving with same angular velocity as that of the object should not observe anything because he is at rest with regards to the object. But unfortunately, as I have shown, the relative speed of energy conservation yields that effect matters, and it matters as much as the Lorentz effect. So that factor 2 effect comes from that effect. So that effect is as important as the Lorentz effect as observed by the outside observer. Einstein has considered the last effect in order to build his analogy, and he did not consider at all. I mean, he gave a thought, in fact, to the other effect, to the effect of the centrifugal field, to centrifugal force, but he hoped that effect would not matter at all. So I can continue, and here is the second part I like to get to. Okay, I hope, Thomas, I gave an appropriate answer to your question. You say also that from the square root of 1 minus... No. That effect doesn't have to do anything with the gravitational world. That effect is applied. I have applied the same effect to the gravitational world. In fact, I have derived the equations for the gravitational world first, and then applied to the Gedanken experimental setup of Einstein. So, I think we have set up the problem, and I see the happy little smiling face of David. I take this as an applaud. Thank you very much for this, David. Now, this is not all. We came to this point in only few 10 minutes, and we have reviewed an entire century, and I hope we have rebuilt an entire century in an hour or so. I hope at least we did. Now we can even derive more based on this approach. Now I'm going to show to you that we can derive the basis of quantum mechanics from this approach, and it's very enthusiastic, I find. So I go back as an example. I can do this anywhere, in fact, based on any example. But let's go back to the spinning disk of Einstein. But this time it's not spinning. We don't find it as spinning. So it's at rest. Everything is at rest at the beginning, and we set the disk to a rotation. So if we do that, then the law of energy conservation, embodying the equivalence of mass and energy, tells us that its rest mass is decreased as much as the centrifugal field intensity is increased, and then at the same time the overall energy is multiplied by the Lorentz factor. So what happens is that when you set up the disk to a rotation, the overall relativistic energy is conserved. It's the beginning. The initial energy, relativistic rest energy, is m sub 0 times c sub 0 square, and it stays constant. It means that the energy you deliver to the object when you get it to a rotational motion is, in fact, to make it ascend to a centrifugal field, just like the case you would descend it to a gravitational field, or you can just think the other way around. If you hire the rest mass from a gravitational field, you have to deliver to it a certain amount of energy. Here we deliver the object to the centrifugal field. So in fact, the energy we deliver, we have to spend is used to extract, to throw out from the object a given rest mass. So in fact, we have over here a clue for the inertia as well. We have written an article for this. We haven't presented it yet. It's coming soon, I hope. So anyhow, the energy we have to deliver to the object is used for its binding. In other words, just think of a reverse operation. So suppose you stop the rotational disks. What you do is you deliver to the object a certain amount of energy. So you restore, in fact, its rest mass. That's what it means. The same occurs for an electric field. The same occurs for a gravitational field. So this is something very general I'm talking about. But let's continue to talk about on the spinning disk example. So if I differentiate the previous equation, which is a constant on the right hand side, the overall relativistic energy is a constant. So I come to this very easy equation. But the binding energy of concern, because of the equivalence of mass, rest mass, and energy, must be equal to the rest mass dumped from the object. So we associate with this rest mass decrease jet speed, if you like. So the mass is thrown out by a certain speed, which I call tangential, wave-like speed. In fact, this is something securing the equality. Securing the law of momentum conservation, nothing else. So these three equations, in fact, so dB, you can bring this over here, and you can bring this expression over here as well. So we can right away find an expression for the velocity. This velocity I have associated with the dumping of rest mass. I'm going to come to it pretty soon, but we have something even more enthusiastic. Let me talk about that before. So rigorously speaking, we can write that equation. I mean the equation of momentum conservation as such, as a vector equation. I mean, so this must solve for a stationary motion, meaning when the spinning rotational motion, the rotational motion of the object has reached a stationary state, then at that stage there shall be no dumping, no further dumping of the rest mass. So we have to have over here 0, but the left hand side is not 0, meaning that the vector u having the same direction as dB vector, it must be infinite. It must be infinite. And I find this extraordinary, and you'll see why. Because we have over here perhaps I can even annul the words, perhaps a concretization of the Mach principle. But the left hand side is anyway finite, so the tangential component of that vector u is equal to this cosine theta times the vector u, theta being the angle the vector u makes with the tangent, and that should still be finite. So this is 0 and this is infinity. Then this tangential component is still a finite quantity. Then we have anyway a finite velocity. But that velocity is what? That velocity is a superluminal velocity. Of course, that velocity cannot carry any energy, because we are dealing with pure special theory of relativity and the law of energy conservation, meaning the relativistic law of energy conservation. So that velocity came from that basis, special theory of relativity and the law of energy conservation. It's still a superluminal velocity, which I like to call a wave-like velocity. Of course, in order to be consistent with the special theory of relativity, I can express it in terms of a Lorentz coefficient times a normal velocity, which can vary between 0 and the velocity of light. And here what then the Lorentz coefficient of concern would turn out to be. Okay, then the thing is, the rest mass variation, say on a circular motion, can well be zero, as I told you. On a stationary motion, it is zero. I just talked about it. So this makes that quantity over here, the Lorentz coefficient times the luminal velocity, which is equal to the tangential velocity I just found, holds as a whole, its entirety. And this is interesting. This is the interesting part of the game, and perhaps embodies a clue to the wave-particle duality. For, as we will see right below, the tangential velocity is the basis of the derivation of the Broglie relationship. So that velocity is the basis of the derivation of the Broglie relationship. I'm going to show it now in just a second. And then the quantum mechanics. So what we are going to land at is quantum mechanics and non-locality, and just through the relativistic low energy conservation, special theory of relativity and the low energy conservation. So note that the greater V, the smaller is the tangential velocity we just derived, but the tangential velocity is never less than c, and vice versa. The smaller V, the greater than tangential velocity. For V is equal to 0, the tangential velocity becomes infinity. And this is the velocity that I'm going to show to be associated with the Broglie relationship. So let's go back to the Brogli's thesis, doctoral thesis. The right-hand side was written by Einstein, m sub 0 c square. H nu sub 0 was written by Planck by the beginning of the 20th century. Einstein even had written this equation, but de Broglie considers this equation from another point of view. In fact, he associates already at rest with the object of rest mass m sub 0 an internal phenomenon, an internal period of motion, to be characterized by the frequency nu sub 0. So that frequency is, on the other hand, associated with a wavelength. If we recall the usual definition of the light speed. So he comes out with this expression for an object at rest. Now, what we do here, we go back to our finding for the wave-like velocity, superluminal wave-like velocity. That superluminal wave-like velocity, let me once again stress the following fact, is induced by the fact that when we bring to a rotational motion an object, its rest mass would get altered, because it is gradually brought to a gravitational, to a centrifugal field. The same would occur in a gravitational field, doesn't matter. So that rest mass variation induces a jet velocity, tangential velocity. I mean, it is just an artifact we can conceive in order to preserve the momentum conservation. But the rest mass is dumped away. So if a rest mass is dumped away, it's normal that we can associate a velocity with it. It's just a rocket, a type of velocity. So the rocket, the object dumps away a certain rest mass with superluminal velocity u. So if now we multiply that superluminal velocity with de Broglie's period of time, or if we divide it by the de Broglie frequency to be associated with the internal motion of the object, then we come to de Broglie wavelength. This is so simple and as much very enthusiastic. So we come to de Broglie's wavelength. So this is de Broglie's wavelength. We arrived at this result by dividing the superluminal velocity we had derived by the internal frequency to be associated with the Broglie internal phenomenon. And this lambda sub 0 is the wavelength to be associated with the internal phenomenon. That's nothing else but the Broglie wavelength. Now, how are we going to conceive this outcome? So, the Brooch wavelength, which is the basis of quantum mechanics, happens to be the wavelength to be associated with a kind of information, or an information we can call, of frequency mu sub 0, which is the original frequency to be associated with internal dynamics of the object at rest, but now propagating with the velocity c squared divided by v times square root of 1 minus v squared divided by c squared. So, in other words, we can write this velocity as the Brooch wavelength times the rest internal frequency of the object. Okay, so mu sub 0 again is the frequency associated with the object's rest mass, but at the given field location. Okay, what we did again is essentially based on energy conservation, and it's fully consistent with the special theory of relativity. The above derivation I just presented is quite general. It can be applied to any field the object interacts with. It holds for any field then, say for electric field, gravitational field, centrifugal field, no matter what field we are dealing with. The superluminal wave-like velocity, the tangential velocity I just derived, constitutes the basis of the Brooch relationship. In order to arrive to the Brooch relationship, all you have to do is to divide this by mu sub 0, the frequency to be associated with the internal dynamics of the object at rest. So, it's after all related with just the velocity of the object of concern. I mean, the superluminal velocity. It leads to quantization since the Brooch relationship, along with the law of energy conservation, is the basis of quantum mechanics. So it is also naturally applicable to a stable circular orbit, to any stable stationary orbit, thus with no mass variation at all. Thus, the interaction of concern, gravitational or electric, or else, must well hold without any energy exchange. This too I find quite enthusiastic. I must confess, the knowledge about the presence of the object of rest mass m sub 0 is propagating with the velocity, we can come to this conclusion, c squared divided by v times square root of 1 minus v squared divided by c squared, which is the superluminal velocity we had just derived, along the given journey. Okay, now to believe that, the way we do in quantum electrodynamics, that the electric interaction occurs via the exchange of virtual photons, is, according to our approach, synonymous with the notion that there is no particle exchange at all. I mean, what are the virtual photons? The virtual photon is just another artifact we introduce, and no one of us understands what it is. So, in fact, there is no energy exchange, then there is no need of any energy exchange. So, the electric charges do sense each other with no energy exchange whatsoever. And that occurs at the superluminal velocity we had just said. And for charged at rest, the superluminal velocity is infinite. Again, to believe that the special theory of relativity allows particles with imaginary mass, was something which was derived by the time I was a graduate student at MIT, so by the beginning of the 1970s, such as tachyons, is the same as the statement that there are no such particles and consequently no mass exchange, were such particles presumed with regards to any kind of exotic interaction. So, similarly, I firmly believe that there seems to be no gravitons, as imagined classically, which are thought to move with the speed of light. In our case, gravitation, null interaction, null information moves with much greater speeds. This is the same as saying gravitons are fictitious interaction exchange particles with no mass, and the gravitation propagates with speeds much higher than the speed of light. And again, as this is something Laplace had discovered by the beginning of 1800s, and I'm terribly amazed that while I did my undergraduate work in France, no one, we studied Laplace very profoundly, but no one had taught to me that Laplace had found that gravitation must occur with a speed at least 109 times greater than the speed of light. Otherwise, Earth would go farther away from the Sun. In fact, twice the distance we have to the Sun, actually, in about 1200 years. And again, all these occur in accordance with this relativistic law of energy conservation. I am almost done, and I will discuss a little bit afterwards. So the gravitation, the gravitational approach we derived, and if in full consistency with the Broglie relationship and quantum mechanics, naturally induces quantum numbers. One can calculate, for instance, the quantum number for the orbit of Earth around the Sun. We come out with this number over here. It's 122 times 10 to the power of 72. This number indeed appears very large, but this affects in no way the validity, presumably, of the foregoing approach. I like to mention that one can derive that Earth, or any object, in fact, at that great numbers, falls down one energy level every rotation. So each year we lose one digit, one number over here. I mean one natural number over here. In 10 years, so this will be multiplied by 10 to minus 1. 10 to minus, yes, indeed. Okay. So, we can calculate the quantum number for the centrifugal case we had dealt with. So we have an object of about 1 gram at the edge of a rotor of about half a meter, making 100 revolutions per second. Then we come out a bound state for the nuclear clock in question, with a gravitational orbit number of 226 10 to the 30. Okay, so here I am at our general conclusions. So the general theory of relativity, which I adored, already based on its monumental analogy, insight, in fact, and which I always had difficulties to understand, in fact, another occurrence, is unfortunately utterly incorrect. Because of the fact that it did not consider the effect of acceleration, the plane acceleration for the rotating disk, in order to state the principle of equivalence, but reduced it to the mere effect of displacement. So Einstein accordingly has unwillingly picked up the pair of length contraction and period of stretching for a rotating disk. This is unfortunately unphysical, as I tried to show. And the correct kernel turns out to be made of both length stretching and period of time stretching. So our redshift is in fact nothing else but quantum mechanical occurrence. It's not geometry, it's not curvature of space. It's simple. The internal dynamics of the object weakens as much as the binding energy it develops when it gets bound to a gravitational field or any field it interacts with, in fact. So the remedy of the principle of equivalence, which is none other than our theory that I presented over here, leaves the general theory of relativity totally obsolete. I'm sorry, but we have to state it bravely. We don't need it. We base everything conversely on the very special theory of relativity and the law of energy conservation. But then we don't need the general theory of relativity. But then we have a totally new horizon, uniting everything we know, and we don't have the micro and the macro worlds to be described with two different and incompatible packages. Okay, so that's what I'm saying. We are present approach. We arrive at just one conception with regards to the description of the micro world and the macro world, thus remedying one of the biggest problems of the contemporary cosmology, we believe. This yields at the same time the derivation of the Brooch wavelength, thus the quantization of any field, including the centrifugal field, not only gravitational field, but centrifugal field as well, of a rotating disk. Our approach also implies a novel concept of interaction without any energy exchange, occurring with speed, with a superluminal speed, meaning speed much greater than the speed of light. I like to call that the wave-like interaction, since our derivation, which is solely based on the law of energy conservation, leads to such a phenomena. In fact, this is nothing but the essence of quantum mechanics. So this sheds light on quantum weirdness and many recent spooky experimental results. So remember that Scientific American's March 2009 issue did bear the following title: Was Einstein wrong? Because apparently quantum mechanics, well, we all know that quantum mechanics involves non-locality, and this is just up to now is felt to be inconsistent with the special theory of relativity. So people started to questioning the special theory of relativity. It's not the special theory of relativity which is wrong, the way the Scientific American asked in its March 2009 issue. It is that the special theory of relativity allows a kind of interaction without any energy exchange, and this is the basis. This is nothing but the basis of quantum mechanics. So we have another question. Ozan warns me. We are privileged to witness this research. Oh, thank you so much, Francis. It's I thank you all. I thank you especially to be so brave. It's hard to hear such flattering comments and criticisms. I'm deeply touched. Thank you so much. So we believe this sheds light on quantum weirdness and many recent, I was saying, spooky experimental results. So it is not that the special theory of relativity and quantum mechanics are incompatible with each other. Quantum mechanics is perfectly fine. The results are well measured. Special theory of relativity is perfectly fine too, and it's tested so well. And we believe in the special theory of relativity. And in that sense, the great mind of Einstein. So it's not that they are inconsistent. It's that I was saying the special theory of relativity simply allows a kind of interaction without any energy exchange. So if an interaction occurs with an energy exchange, such as that embodied by the exchange of electromagnetic radiation, then that kind of interaction cannot occur with a speed greater than the speed of light. But what we came to is that an interaction can occur without any energy exchange. I believe I have proven fairly this point. Then that kind of interaction occurs with speeds much greater than the speed of light. And in fact, for instance, electric charges sitting at rest with regards to each other, that kind of interaction occurs, or for two rest masses sitting at rest with regards to each other, that kind of interaction occurs at with an infinite speed. So the special theory of relativity and quantum mechanics are well compatible with each other. There is another remark. As pointed, okay. Bob Care too says that he agrees. Thank you very much to Bob. So what I did what we did not know so far, let me summarize, is that the special theory of relativity in fact allows an interaction type without any mass or energy exchange, and that at superluminal speeds, and this is in fact what quantum mechanics is all about. And we have still difficulties to publish some of our results, but we did publish quite a number of results in mainstream journals as well. But I have to confess that we had to struggle a lot. So, but at the same time, I come to another enthusiastic point. I find this was one of my discoveries about 10 years ago, even before I knew the data. So the idea I had developed with my friends, with my colleagues, and I have presented to you in the past an hour or so, induces the fact that an electron bound to a nucleus should also experience a rest mass decrease. So this would result, this would yield just the kind of metric change I just presented. So the electrons' internal dynamics should get weakened as much. Of course, unfortunately, the physicists are not accustomed to talk about the internal dynamics of the electron, because they take the electron as a point-like particle, and the reason they do that is simply that otherwise the electron's charge would deteriorate each other, so that the electron would disintegrate. So in order to prevent this occurrence to happen, they think they had considered the electron as a point-like particle, but to me as an engineer, as a nuclear engineer, it's pointless to consider anything as point-like. That means that there should be nothing in a point. Nothing can reside in a point. So the electron must have an internal dynamics, and that inside dynamics should get weakened when bound to an electron to a nucleus. So then the electron must also exhibit a kind of motion around the nucleus, and we know that the momentum, the momentum of the electrons, the distribution of the momentum can be measured, so we can well associate a motion with the electron. So the internal dynamics is weakened for the bound electron. Its size should get stretched. It's because its internal dynamics is weakened, then it's the period of time to be associated with that internal dynamics should get stretched. Of course, we have no way of measuring that with the electron, because it's a stable particle. So far we have no way of detecting it, but we can measure whether this approach is correct or not. For the electron with a muon instead of an electron. So suppose we have a bound muon to a nucleus. So here we have the bound muon retardation time, and one is for the muon at rest. And here is the Z, the number of the number of protons in the nucleus. And I hold the privilege to have predicted that the bound muon decay rate retardation must decrease with Z, with increasing Z. This figure was recently redrawn by my dear colleague Professor Alexander Kholmetskii, and here are the results, striking results. So don't worry about this background scattering over here; it doesn't mean anything. So here are the data. These are the data. Quite a huge, cumbersome kind of approach had been developed by Hoof and his colleagues some perhaps 20 or 30 years ago. But our prediction is clearly much better than their prediction. So it states that the bound muon rest mass is decreased, and its internal period, the internal dynamics weakens as much, and its internal motion slows down, meaning that the bound muon should decay in a more difficult way than the free muon. And as the number of protons increases, then the muon is bound even more severely to the nucleus, then its half-life becomes even longer and longer. So so this is another example showing that we are well capable to describe both the microworld and the macroworld with the same tools. In fact, this tool is nothing else but the relativistic law of energy conservation. This is kind of striking, amazing. I mean, the law of energy conservation was in front of us since Lavoisier. And special theory of relativity was there, and all we did, in fact, could have been derived perhaps 100 years ago. Very unfortunately, although I have to state my admiration towards Einstein's special theory of relativity. Unfortunately, the way he started the general theory of relativity was based on a non-conform analogy, and we believe led him and the science world to invalid and irremediable results. So I can conjecture the following to conclude with regards to the gravitational waves, so-called gravitational waves. In fact, although the energy is conserved, say, in an orbit, in the atom, or in the solar system, as we have shown, this can be handled exactly by the same tools, or elsewhere in a celestial closed system. Because energy by nature aims to get minimized, the electron or the planet on the level other than the ground level tends to get closer and closer to the attraction center, here assumed for simplicity infinitely more massive than the companion in question. This is not a necessity, as Professor Sobzik, Dear Garrett, and I have shown in a paper we have last year published in Journal of Applied Computational and Applied Mathematics. We then have a situation fully in accordance with Bohr's postulate, that is, the electron or the same planet radiates only if it jumps to a lower state. And all other things being equal, it should, perhaps following a complete rotation, which I also hold the privilege of showing, keep on jumping to lower states until it reaches the ground state as induced by the minimum energy requirement. And this is, to our understanding, the cause for which the binary system, for instance, the two stars rotating around each other gets closer and closer to each other. And perhaps, I mean, if you like to call it gravitational waves, you may like to call it, but this is nothing other than a gravitational radiation. Well, thank you to all. Dear David, I'm done, and I'm kind of ready to answer any questions to be introduced by our colleagues.
Okay. Thank you very much. You can hear me. There is a long delay, so everybody remember that. You hear me there?
I do hear you.
Okay. Well, thank you very much. When I come back, I have to switch, unfortunately, to my video microphone, so that's not as good. But thank you so. Okay, thank you very much for the great and informative talk. I think it's very an innovative theory about how general relativity is not correct. I think that for me, I've not seen this type of argument for the problems with general relativity before. I've seen a lot of evidence against it, for instance, with Dr. Dowdy, Edward Dowdy from NASA, who does not see, in fact, evidence for general relativity. So that's very good. Before we open it up here to questions, I do have a couple questions myself. I think it's very interesting. I have not met many scientists who actually say that general relativity is wrong, but special relativity is right. And I'd like to have you address a few questions as to special relativity. Number one, you said that special relativity is well tested. I'd like to know where you're saying how that is. Two more comments is Ron Hatch. I don't know if you're familiar with his work. He is a GPS scientist and does calculations with GPS all the time. He's got 15 patents in that area. Has made a lot of money actually in that area, and he's very well known in that area. And he says that special relativity is not correct. Also, in my film Einstein Wrong, I have a Stanford linear accelerator scientist, actually a mainstream scientist, saying that mass increase is not observed in particle accelerators, which a lot of us who study this area know that's true. And also, I have Dr. Karazani, who's Argentinian physicist, who did some, I think, brilliant work on showing what actually is conceptually wrong with special relativity, and that is you cannot have more than one frame in the universe. You really only have one three-dimensional space. So I guess my question in general is, you say special relativity is well tested, but how would you explain Ron Hatch and GPS and the Stanford Linear Accelerator. Mainstream scientists and unmainstream scientists do know that they do not observe mass increase in particle accelerators. I'm just curious, how do you deal with that, those notions from other scientists in the field?
Okay, thank you very much for the question. For me, the special theory of relativity is nothing else but the constancy of the speed of light as referred to different frames of reference, Galilean frames of reference, meaning frames of reference moving with a uniform translational velocity with regards to each other. There's one thing. The second one is the Galilean principle of relativity, meaning that in a uniform translational motion, you have no way of detecting your speed with respect to, say, distant stars by just performing any experiment inside of your vehicle. So in fact, I think we are being unfair towards Galileo. Galileo was the first one who introduced that Galilean principle of relativity, and Einstein, in fact, not to reject any of these two experimental phenomena, then had to, I mean, if you see the equations, you only have to play with the space and the time entering the equations. So for me, the special theory of relativity is based on these two experimental observations. Now, in my approach, though, in our approach, the speed of light, there is a ceiling, C, if you like, but the speed of light, although perhaps very, very close to C for any photon energy, is not really C. It should be a little bit below C. But C is perhaps a property to be associated with space, the empty space out there, or whatever. And we cannot call it empty, of course, it's not empty. We are used to call it empty space. So for me, that's it. And for me, again, as a nuclear scientist, special theory of relativity is the equivalence of, as a result of mass and energy, and there is a very easy way of testing it. You produce energy in a nuclear power plant, say 1,000 megawatt electric power plant, so you have to multiply this by 3 to obtain the power, thermal power. So in a year, you have to convert into energy about 1 kilogram of mass, and that can be measured. I mean, you can weigh, so you can start a nuclear power plant of 1,000 megawatt with 1 ton of plutonium. At the end of the year, you can weigh that 1 ton. You will find 1 kilogram less. So for me, the special theory of relativity is nothing else but that. And I mean, we can argue, of course, but what I use throughout is nothing but the mass and energy equivalence of the special theory of relativity. I also use the Lorentz
Harry,
time
do you want
dilation
a
factor.
microphone? Normally he does.
I think measurements
Would you like
tell
a microphone,
more.
Harry?
Will tell us more. We believe over here we have a full, harmonious, complete way of looking both the celestial world and the atomic world. Okay, so someone has got. Who told me, Ozan? Something. Harry Ricker. Oh, yeah, okay. No, okay, Harry says, okay, thank you very much for the introduction of that question, dear Harry. Now you...
Harry, do you want a microphone?
I have his question over here. He says...
Would you like a microphone, Harry?
Shall I continue? I have his question over here written. Shall I continue to answer? Now he says, Harry says that we base our entire argument on the assumption that length expands contrary to what the special theory of relativity asserts. Not really. Now we have to understand these points very well. I have no problem. We have no problem with the special theory of relativity as long as the object in question moves and then the length contracts. But when the object is brought to a say, gravitational field, its less mass decreases. The same occurs for the centrifugal field. Now, this length stretching comes out along with this process. So, length stretching is accompanied with mass decrease. So, when you spin out, when you rotate the object, so the two combines, and I can affirm that the length stretching along the rotational tangential direction is compensated by the Lorentz contraction. So there is no length, overall speaking, there is no length change at all along the tangential displacement. So I think I have an answer over here to Harry's question. I don't contradict at all the special theory of relativity. This is induced by the mass and energy equivalence of the special theory of relativity.
A couple comments.
When a mass decreases based on the special theory of relativity,
I'm listening to what you're saying.
The length,
there's
the size of the object of concern
in my opinion,
stretches. Meaning, if you bring the hydrogen atom to the surface of the sun, then its size stretches. So, if furthermore that hydrogen atom rotates with the sun, then its size for us, for observers, distant observers, shall get contracted along the directional portion. So, these are two different phenomena, but the length stretching is induced by the mass and energy equivalence of the special theory of relativity, and it's fully compatible with the special theory of relativity.
The underlying assumptions of what Einstein
Paul has got a question, I think. Do you mean that they have not observed gravitational mass increase in particle accelerators? Oh, the question goes to your colleague, I think, David.
Are observational equations and not the reality.
Paul is quite correct for me, because mass increases in the following way in particle accelerators. So you accelerate particles, you deliver them energy, and then you make them collide. Then you end up with much heavier particles. So that's a way of condensation of energy, kinetic energy into less mass. So that's the answer of your second question as well, dear David.
They are using Okay, I just have a couple comments. I'm listening to what you're saying, and there's a couple of things. I think there, in my opinion, I think there's maybe a different interpretation of what you're saying, and I find this often sometimes with dissidents. When you talk about relativity being okay, I think there's some. I would like to see what are for what you're doing on that, because what I'm saying is a couple of things. One is many people who say special relativity has some merit or some validity are really changing the underlying assumptions of what Einstein was talking about, and that's Karazani's work. As particles, I'm sorry, but regardless, when you're talking about the accelerators. What happens is, as you're accelerating particles, and there is no mass increase, there's obviously kinetic energy increase. At the end game, they are using relativistic kinematics, and when they use relativistic kinematics, they also introduce the neutrino, and then of course what you do is have two wrongs make a right, using relativistic kinematics at the end and introducing neutrino, which is actually a way to save conservation. You end up having 1 plus 1 minus 1 equal 1. And so it's a sort of unnecessary. So I think my comment is,
when I hear you talk about the areas I've studied a lot for the last 15 years, I am interpreting what you're saying as being very different from what Einstein says what special relativity is. I also, I'm not sure you're aware of some of the explanations of the kinematic equations being circular, meaning if you use them, you have to have the neutrino. If you don't use them, you don't need to have that. Muon decay also can be explained without time. That's just a comment. The question to you is maybe to your talk, again, a little confused on your relativity talk, is that do you believe in time dilation? Time dilation is that time itself changes, or are you one to say that clocks themselves change? Do you believe in universal time?
Good question. Well,
okay,
we scientists are bound to talk about what we can measure.
I know you said you answered the question, but I still just didn't get a yes or no. I guess
in fact,
I interpret your answer to the second postulate
we have a phenomenon,
as being, yes, you
phenomenon.
believe that all observers, no matter what their relative velocities, will measure C.
Then the atomic molecule vibrates, and you can compare the number of vibrations with another phenomenon occurring next to the atomic molecule, and you can count 1, 2, and 3, and 4, and 5, and 6, and you can say, well, okay, this vibrated about so many times, and that phenomenon next occurred. So time is not something we have to worship. Time is something associated with a phenomenon that can repeat itself, or we believe does repeat itself regularly. So, for instance, I have shown to you the muon decay rate retardation. So, a muon has got a decay rate. So half-life. So it means that if we have, suppose the half-life is about 100 units something, if we have a given number of muon at now, it means that we will have half of it throughout a period of time which is equal to its half-life. So that's what time means. So that half-life, I have shown to you that for bound muon is altered. If you are bound to the bound muon, then you will measure the time with its decay rate. So our time are in bound muons here not bound to any nuclei, and bound muons bound to nuclei do not decay the same way. So then we can talk about etalon time for a location of space free of any field. Fine, I agree with that. And then supposing that you are at rest with regards to distant stars,
okay. Do we have any
as well.
Questions?
So you can talk about that kind of time. But otherwise, your period of time changes when your units, your muons, for instance, are bound to a gravitational field or to an electric field,
or
they are speeding up with regards to distant stars. That's what I mean.
In my opinion, I'm not
Garrett says Minkowski space-time. You said something else, David. What is space-time? What is space-time? Okay. What is space-time? Okay, great.
In my understanding, seem to be conflicting with that statement. So,
what is space-time?
In my opinion, I think that's
okay.
I'm
for me,
that part. I think the general relativity stuff is very good.
You have a structure.
And also,
okay.
I think your attitude, obviously, the engineering attitude is
visualizing the atomic molecules
things are very commendable.
Shall provide a good example.
On the special
relativity side, we have a atomic molecule. Say we have a lithium-2 molecule. That molecule has got three basic properties, as I explained throughout my talk. So the first one is the average internuclear distance. So it's the distance in our laboratory frame of reference between the nuclei. The second characteristic the atomic molecule displays is the period of time. we can measure it with respect to another clock we have in the laboratory frame of reference. So we can only compare. You can only measure a quantity in terms of a unit you define in the world of that quantity belongs to. You cannot measure anything with any unit which does not belong to the world that quantity belongs to. So the third property that the diatomic molecule displays is the clock mass, as I call. So in our example, it becomes the reduced mass of nuclei. So these are the three quantities. So space, time, and mass, in fact. So when I call mass, I call clock mass. When I say space, I mean the size in question.
Well, no. I mean, again,
when I call time, I mean the period of time, the phenomenon of question displays. Okay, now you can move this diatomic molecule onto a uniform translational motion, or you can bring it to a gravitational field. And now you can compare what happens as compared to your another diatomic molecule, a twin of the previous one, in a space free of any field and at rest. And then what you see is that the diatomic molecule slows down in the field of concern. Or if that diatomic molecule makes a turn in space,
more in an area.
Under the circles,
the only thing, like I said,
rotational turn, but the radius of that orbit may be very, very large, and then comes back, is brought back, and when you compare what happens to that diatomic molecule with your twin diatomic molecule sitting with you in the laboratory frame, then you will observe that the number of ticks that it displays is lower than the number of ticks that your diatomic molecule in the laboratory frame display. That's all. I mean, space and time is for me, space is size, and time for me is the period of time to be associated with a given motion. That's all. I mean, I think we have to have our feet on the ground, and we have to be very concrete. And we don't have to worship time or whatever. And I think I was able to show to you that these three quantities, these three concepts, these three quantities, meaning clock mass, clock size, and clock period of time, they have to be structured in just a given way. Now, if you ask me, based on my experience, what is your basic quantity? I mean, what makes all that? It's Planck constant.
Time itself is,
I mean,
and I understand your idea of
this is a given architecture.
I agree with you on that.
The simple entities, the elementary entities, do not get combined in a random way.
A lot of things you say are sort of in agreement with that.
They just get structured, and they just bring themselves to upper levels of organization in just a given way. So that
things that you say don't
size and mass,
that's where I'm getting confused.
If I say to take a shortcut, and time, meaning period of time, and space size, and mass, clock mass, carrying out the labor, clock labor, they are architectured in just a given way. What is that way? That way is the following. So if you have in front of you the quantum mechanical description of that entity, it means that any change of the rest masses entering that description, quantum mechanical description, will yield to a parallel description of the eigenvalue, meaning the total energy of the entity, as much. Well, then also the size change of that entity, the same all over. So this is what I call the universal matter architecture. So this is in fact the basis of the end results of the general theory of relativity. I'm saying, well, not the general theory of relativity, but the end results of the general theory of relativity, and this is the basis of the end results of the special theory of relativity. David says, okay, let me go back with this. What I'm saying is that any entity has got three basic quantities we can describe the entity in terms of. So I'm talking about this entity. I mean, suppose we have.
Yes, I'm familiar with that.
To change the example, suppose we have
retardation.
The hydrogen atom.
That's not time dilation.
the hydrogen atom is made of the proton and electron, if we like to conceive it the way Bohr did, and the electron rotates around the proton. So the electron displays a period of time. It's about
now we're getting
2,000 kilometers per
somewhere.
second.
Because
that entity has got a size. It is about 1 angstrom.
That's changing a basic
in fact,
assumption.
0.5
I think we're getting
angstrom, half an angstrom.
Clock retardation.
This is the size of the average size of the hydrogen atom.
Community
and there's a clock mass. It is the mass in this example of the electron. Electron rotates, so it carries the clock label. I know that these are new terms, and
retardation changes, and
I like to be patient so that I can forward my thinking about it.
Perhaps.
So,
it is a terminology problem.
So these three quantities,
if you take a clock
space, time, and mass, in short. But in details, when I say space, I mean the size of the object. Measured in terms of unit length. It can be centimeter, it can be angstrom, it can be anything. So the time meaning the period of time. It can be measured in terms of rotation per second. It is the period of time one rotation takes. And mass, the clock mass is the electron mass. So they ought to be structured in just a given way. For the case of the Bohr atom, it is that the period of time is equal to 4 pi squared divided by h times the quantum number. Then the electron mass times the square of the size. But that's kernel, architectural kernel holds for every object. That's what I'm saying, and I have drawn a whole new schematic about the diatomic molecules. It holds for diatomic molecules. It holds for everything. So mass and time and size ought to be structured in just a given way. Indeed, that's another way of. This is my way of interpreting, as we just pointed to special theory of relativity, even the end results of the general theory of relativity. So matter has to be built in just a given way. Because it is built that way, then we have the end result of the special theory of relativity. Or, in fact, more profoundly, the Galilean principle of relativity. That's what we have. It means that we have no way of measuring how fast we are moving in a vehicle, moving with a uniform translational speed with regards to distant stars, by just performing experiments within our vehicle. So because the Galilean principle of relativity holds, then matter has to be built in just a given way. Or vice versa. Again, because matter is built this way, the Galilean principle of relativity holds. Or if we go back to the interaction of
what happens
any
is
such
time. What happens? I understand what you're saying.
The gravitational
First
field,
of all,
because we have the measured end results
in general,
of
I'm not disagreeing with.
I
think you have an amazing
then again,
attitude towards science, and that's why you've gotten so far
in just a given way, and the
things.
way I have described. Or the other way around, because we have those results, then we come back,
I know
of course,
that
our way
measuring and the physicality of measuring, that is absolutely true. We have to use clocks, and there's an engineering point of view.
The creation assumes altogether and at the same time, conjointly, both the elementary particles and the architectural.
What I'm saying again is I think that measuring time is
the architectural
actually having
structures.
This idea that
in fact, this structure, the architectural universal matter architecture,
relativity a lot
making
closer. You were working general relativity. I have not studied
how
that as much.
This matter is going to
the idea again is that
build itself.
Time itself. We hear that all the time. Time
upper organizational levels.
That is
so
that
the crystal
comes from the idea that you
oscillation
have to, even
is not
though
any
you have
different.
A single source,
Again, matter, space, and size are architectural in
observers,
just the same way.
Those
The
people
crystal,
all would have
the
to
quartz
measure
crystal,
that.
for instance,
And then there's two things that
making
happen.
your
Either
watch,
people say no, special relativity really
on
isn't
your
that.
arm,
It's
on
really
your,
more of measuring type of theory.
you
But
use,
again, you change the underlying
as a watch, it's just made the same way. So matter is architected just the same way.
They say
So
time
this is
itself
what
changes,
I
not
wanted
the
to
clock
convey
that's
to
ticking
you.
away. So I think that's the only thing I would say
So this
is for you to
so everything fits
be
beautifully.
careful in that
So quantum
terminology,
mechanics
in my opinion, because those of us who look at
is
that kind of terminology
special
will
theory of
get
relativity is
get
David
us
has
confused
another
because
question.
we've made the very clear distinction between
Do you
time
believe
itself
that the
and
two
again
postulate
the
of
measuring
special
of time, which
theory
you
of
are
relativity are correct?
absolutely correct. You and Borchert
it's a good question.
I'm a great fan
Now,
of Borchert's work.
the
He said
two
that time is motion.
postulates of the general theory of relativity.
That's
the first one, I think, it is the Galilean principle of relativity. I find this very profound.
Which you can't really ever
the Galilean principle of relativity. Meaning again, I hate to repeat, but I like to make things clear. The Galilean principle of relativity, established by Galileo some 400 years ago, says that you have no way of detecting how fast you are cruising on a uniform translational motion with respect to distant stars, for instance. We are just performing experiments within your vehicle and without receiving any information from the outside. So that principle of Galileo, I think, is fantastic. I'm amazed by it, and I believe in it. And the other postulate, the other postulate is the constancy of the speed of light with regards to uniformly moving frames of reference with regards to each other. This also seems to be tested quite severely. As I'm saying, light speed may change from one energy photon to another photon energy. So light can get faster if the photon energy increases. But so far, we have no way of telling it. But I can affirm for you that the gravitational theory we have developed with my colleagues, and dear Gerrit is over here. So he has been my colleague, and I'm grateful to him. Does not assume any particularity either for mass or ordinary object. For me, for us, light behaves just like any ordinary object. And this is the basis of quantum mechanics as well. Light and any ordinary object doesn't matter. And we have a theory of gravitation valid for both light, meaning the diffraction of light is YARK by that theory, and for any object. The theory does not make any differentiation between light and ordinary matter.
Well, listen, I want to thank you for, I think we're going to stop the recording.
Okay, Ozan warned me again
and
with
all
respect to
inviting
David's
so many people along.
question.
Garrett
Now,
and everybody.
if you have
it's very great to have
uniformly
all your
moving
colleagues.
frames
In
of
fact, we've
reference
added
with
a
respect
couple
to
new
each other,
people. We've added Garrett.
the Galilean principle of relativity itself forbids that the light speed is not the same.
I think, again, I congratulate you on...
Let me put it the other way around. There is a ceiling, which we call C, as light velocity. You may like to call it light velocity or not, but that speed must be the same as the Galilean principle of relativity teaches us. So if that speed is not constant with respect to frames of references moving with a uniform translation velocity with respect to each other, then the Galilean principle of relativity breaks down. So the fundamental question to be asked is, I think, whether the Galilean principle of relativity is correct or not. To my understanding, the Galilean principle of relativity is fundamental
and so I want to applaud you on that
correct.
attitude. I want to also congratulate you on your
Harris,
fighting for these ideas, because I think
David first,
I've heard from you. You've had struggles like anybody else, but I will tell you,
says that I assume an absolute state of rest.
In our group. We have people
which you
who
say
like
that
mine,
it is an
and that's what
impossible
the
state
idea
based
here.
on special theory
I
of
really
relativity.
would hope to hear you again.
No,
have you speak again and continue your work. And I also would invite you to join in some of
I'm talking about
other speakers, because I think
to answer
what's
this question,
really important now is we have a way for all of us.
there is one
as you know,
rest
always
frame
coming against
of
the
reference,
wall of the
which is
mainstream
your frame of
trying to
reference.
I think I've come to the simple
Provided that you are not in any
never
field.
change about those things.
Even
So I think
if you are
we are now
in
finally
a given
gathering,
field,
finding
you can
ourselves.
still.
Let's all work together.
Let's find our we could show that
Let's
that
also
frame,
learn from each other and adjust
in fact,
our own ideas
does
according
what
to a lot of other people's work.
the uniform
I know a lot of my
translational
ideas
motion
have
does
changed,
to the object.
just by
So,
listening
no,
to people
we
like
have
yourself,
that frame of
a year
reference
ago,
if you are free of any field.
Relativity was completely
Harry
wrong.
says that your theory is
Predictions,
inconsistent with Galilean principle of relativity.
Numbers of people.
No,
and,
I don't assume absolute rest. I only assume rest.
Changed my ideas, but I think
I only assume rest.
So I want to thank you, and if you
But
want to make any concluding remarks
when you deal with a gravitational field,
you can do so,
or with a centrifugal field, I don't assume an absolute rest.
So if you
I
have
assume
any concluding remarks,
a field, a location free of any field. In the centrifugal field, I'm going to come to Harry's last question. In the centrifugal field, your rest frame is free of any field is the center of the disk, assuming that you rotate with the same angular velocity as that of the disk. So in a gravitational world, your rest frame is again the infinite. I mean, you're infinitely away from the celestial body. Otherwise, your disk can move with respect to another frame of reference, but you can still be at the center of that disk and at your free frame, at your reference frame of reference at rest. Okay, so Harry says that I like to get your answer. Is C is measured the same for okay, so Harry says in order to say that rest mass decreases, you have to have some rest state to say the rest mass decrease. Okay, yes. Okay, so suppose you conclude. I mean, your rest mass is the rest mass in that frame of reference. Your disk frame may move. Your disk frame at the same time may be a rotating frame for the object at the edge of it. But as you stay at the center of the disk, you may be moving with regards to an outside observer on a translational motion, but then you are at your rest frame with respect to the object in that centrifugal field, I mean. I hope I was able to convince. So David says, I like to get your answer to Tolga. Is C measured the same for all observers, no matter the relative velocity? That is the basis of the second postulate. Well, as please allow me to repeat, and I will come to the next question. What I understand is the following. If the Galilean principle of relativity is correct, meaning that you have no way of measuring your velocity, your uniform translational velocity is referred to an outside, to a distant star, for instance, via just performing any experiment inside of your vehicle, then your velocity and velocities, velocities of light with respect to frames of reference moving with a uniform translational velocity with regards to each other may be constant. Yes, but this is a result. This is a result yielded by the Galilean principle of relativity. Okay, if I am allowed to come to the next question, interesting experiment with the centrifugal anisotope. You have presented a point of view I never considered. I like your theory, Tolga. Thanks, bye-bye, he says. And I thank very much Dr. Richard Jesh. And I'm ready to answer any other question if you have any.
Okay, does anybody else want a microphone? I know you said you answered the question, but I still just didn't get a yes or no. I guess I interpret your answer to the second postulate as being yes, you believe that all observers, no matter what their relative velocities, will measure C. Is that correct? Did I interpret your answer correctly?
Yes. In their frames of reference, they are going to measure C is just a number. C, how can you measure C? You have to compare to another speed. You have to compare to the ticks per second of a diatomic molecule. So the diatomic molecule will slow down, as referred to an outside observer, as much as C, in fact. So while you are imprisoned in your frame of reference, yes, indeed, you'll come out with that particular number C. Okay, Thomas says, Tolga, yes, the velocity of light is constant in all frames because it moves by its own bootstraps. A photon generates its own motion. This is a peculiar comment. But let me one more time affirm that in this approach, C is just a ceiling, and this is to say that whether we deal with light photon, or any ordinary matter object, doesn't matter really. So as you may recall, nowhere in this presentation I talked about the particular behavior of light. I have not talked about light at all throughout the entire talk. We agree about that. Why? The reason is simple, because light, according to this approach, is just an ordinary object. Light, I mean, the reason we think of light as a peculiar and different special object is that we first see light when we open our eyes, and mankind has had to deal with light first before everything else, because he saw light, that's all. But in this approach, I have never said light. Nowhere in the approach you will find the word of light. And quite on the contrary, light and any ordinary object behaves just the same. And this is the basis of quantum mechanics as well. We don't differentiate between light and any ordinary object. Although we have a ceiling, a speed ceiling C, and we can affirm that any light photon moves with a speed very, very close to that ceiling speed, whatever is its energy. Whether it's very low or it's very high, presumably that a light photon will move faster when its energy is increased as compared to a lower energy photon. But so far, the instruments could not detect such an outcome. But anyway, once again, for me, light is just any ordinary object. And nowhere in this presentation I stated especially light. I did not make any differentiation between light and any ordinary object. And we can of course talk about the inside dynamics of a light photon as well. This is something else. We can do that. But for instance, the diffraction of light nearby a celestial body and the diffraction of any other object, say a planet nearby the sun, are handled just the same way according to this approach. And we can arrive to the de Broglie relationship just the same way based on any field. Then we come with that superluminal velocity. It can be, of course, extended and extrapolated to any object moving with a given speed in a space with no field whatsoever. Any other question?
Okay. Do we have any other questions for
Okay.
Tolga?
Dear Thomas says, okay, thank you very much, Thomas. Apparently I was able to convince.
Well, I personally, I think there is some confusion, in my opinion. I'm not understanding your explanations as regarding to saying is okay and is fine, yet things in my understanding seem to be conflicting with that statement. So, and maybe in my opinion, I think I'm still not getting that part. I think the general relativity stuff is very good, and also I think your attitude, obviously the engineering attitude, is those things are very commendable. I'm just on the special relativity side. I'm confused again because I've studied a lot about that, and so I'm hearing a lot of times one statement that conflicts with another in an assumption, and it's just.
Please.
But that's okay. That's what we're here to, is to try to understand and discuss. But do we have any more people would like to have some questions answered? We are coming up to about We're coming up to about 10 o'clock a.m. here, so we're about 2.5 hours in.
I would love to be able to try to continue to answer your question if you like to formulate it once again, dear David. And I have a question over here by Bob Kerr. The reality is the fact that he says simultaneous frequencies can only be transmitted at the same velocities. Okay, I mean, but David, if you care to reformulate your worries or points or conflicting points, I love to continue to a little bit try to continue to answer.
Yeah, well, no. I mean, again, I commend your work. I'm a big fan of a lot of your work. It just happens that one of the things we have to remember in our dissonant world we're discovering from all of our meetings is we have a lot of people who spend a lot of time thinking about each part of these problems in physics, and I commend you for bringing even a new perspective for me on general relativity and its problems. In discussions with other scientists and dissidents, we all have to understand that our own understandings many times of even in our own work can be clarified or even enhanced by others who've worked more in an area. And I'm the only thing, like I said, I'm getting, for instance, the simple questions of where we have people who use GPS, and if you put another frame of reference, is the moment the GPS people put a frame of reference in the middle of the Earth where they are measuring from, and they put a second frame of reference on the satellite, nothing works. What they find is they keep the center of the reference point in the middle of the Earth, and everything from there is. And I think the only thing I'm not understanding is, okay, when we have evidence even in GPS that it doesn't work at all, and that another thing is whether or not there's consistency with the idea that. The other thing I think that's bothering me is my question about the second postulate of special relativity says the reason their time dilation comes up at all is because Einstein said that you have to measure the speed of light the same, even from the same source, even though the relative speeds are different. And that, to me, is an absurd statement, and then causes us to say that the physicality of time itself, this idea, and I understand your idea of measurement of time. I think I agree with you on that. The postulate of relativity is its downfall. It is absolutely wrong, in my opinion. And a lot of things you say are sort of in agreement with that. Okay, so the basic assumptions of relativity, I hear. If you agree with special relativity, you have to agree with those assumptions. Yet things that you say don't seem to agree with that. So that's where I'm getting confused.
Okay, I think I see your point. So, but for me, I mean the time dilation. I hope you are hearing me. The time dilation is nothing else. I mean, you just take a look at, just consider a photon clock, meaning you have two mirrors in between which a photon goes back and forth. Okay, so now you move this clock, a photon clock, in a direction perpendicular to the photon motion inside of the clock. So what happens is that, according to the outside observer, the speed of light will remain the same. The photon speed will remain the same. Yet now the photon will cross will have to cross a longer distance. So the number of ticks is referred to the number of ticks to be registered with the twin clock at rest with you in the laboratory frame will get slow, will be lower. That's nothing else but the time dilation, or the time dilation is nothing else but that. So the time dilation.
Yes, I'm familiar with that experiment.
Okay,
but that's clock retardation.
Okay, so
that's not time dilation.
For me, clock retardation and time dilation are the same. David, let's try to make this point clear. For me, the clock retardation.
Okay. Now we're getting somewhere. No, but we're getting somewhere because that's changing a basic that's changing a basic assumption. So I think we're getting somewhere. Clock retardation, according to almost everybody in the dissident community, is not at all the same as time dilation. In my understanding, special relativity says that the actual idea of time changes, whereas what you're saying is clock retardation changes. And to me, a clock slowing down is not time dilation.
Well, I see what you mean.
You and I are in disagreement. To me, it's a terminology problem, perhaps. But if it is a terminology problem, what happens is that if you take a clock and freeze it, it stops. Or you take a clock and put it up in lower gravity, and it's going to go slower. But what I'm saying is that in the dissident community, and I've been around the dissident community over 10 years now, we all are sort of 90 or more percent everybody agrees that clock retardation and time dilation are in fact not the same concept.
Okay, I see what you are coming at. Okay, thank you very much for this remark. But for me, there is no time if you have no motion. So if you have no clock, then you have no time. I mean, it's to me it's absurd to talk about any time without any clock, meaning any motion that can repeat itself regularly. So it's absurd to talk of any time without having this kind of regularly repeating motion. So that can be a pendulum, that can be a vibrating diatomic molecule. So then any retardation is associated with such a clock, of course. And I mean, otherwise there is no time or no quantity we can worship, really. I mean, to time, I understand and I agree with you. But I cannot talk about anything I cannot touch. I cannot talk of anything I cannot, which is not concrete for me. So you cannot measure any quantity, including time, without choosing a unit belonging to the world that quantity belongs to. So you cannot measure a distance without picking up a unit belonging to the world of measure of distances. So you cannot talk of any period of time without picking up a period of time belonging to the to the world
I think a lot of us
who've
looked at the same thing.
Yeah, okay.
Is I think that the time is but that what happened is this time. What happens? I understand what you're saying. First of all, we're in general. I'm not disagreeing with. I think you have an amazing attitude towards science, and that's why you've gotten so far and done a lot of great things. I apologize for the background noise, but
great. I enjoy that background noise.
Right now, but what I would say is that again, there is a difference. I know that measuring and the physicality of measuring, that is absolutely true. We have to use clocks, and that's an engineering point of view. But I think. Okay, I'm sorry, it's just my microphone. But what I'm saying again is I think that measuring time is one thing, but actually having this idea that, at least again, a lot of us who studied special relativity a lot closer, you were working general relativity, I have not studied that as much, but in special relativity, the idea again is that time itself, we hear that all the time, time itself is changing, and that comes from the idea that you have to, even though you have a single source, that in multiple quote-unquote frames or multiple observers, those people all would have to measure that. And then there's two things that happen. Either people say, no, special relativity really isn't that, it's really more of measuring type of theory, but again, you change the underlying assumption. When Einstein and everybody who talks about Einstein look at it, they say time itself changes, not the clock that's ticking away. So I think that's the only thing I would say is for you to, because those of us who look at that kind of terminology will get us confused, because we've made a very clear distinction between time itself and, again, the measuring of time, which you are absolutely correct. You and Borchert, a great fan of Borchert's work, he said that time is motion. Absolutely. That's the physicality of it. But the idea of time itself or space itself, which you can't really ever sort of define, Einstein said that's what really is changing. It's not it's not the clocks, it's not the measuring, it's not the physical things. So I'm just saying that in our community, those of us who study that's going to confuse us every time. To say that clock retardation and time dilation are the same is going to confuse us, a lot of us.
I mean, not to leave this unanswered, I'd like to talk about, I understand what you say, about the period of time and time which is moment, the instantaneous time, period of time, just like location and piece of land, distance. So location is just a point. Distance is the land between two locations. So just the same way we can define a moment overlapping with a given action, with a given phenomenon, and we can define another moment overlapping with another given phenomenon. Then you can talk about the distance between these two phenomena, which is the period of time. So for me, there is nothing. I mean, I mean, otherwise we are going to talk about metaphysics. I agree with you. We should not worship quantities such as time, and we should only talk about concepts and quantities we can measure or we can finally pin to be measured. So, okay, a moment and a period of time are of course different, just like a point, a location, and a distance are different from each other. And indeed, in that sense, there is that we may talk about the relativity of simultaneity as referred to different frames of reference moving with a uniform translational motion with regards to each other. The same occurs with regards to a field, say with regards to a gravitational field. But then, when we talk about periods of time, sizes and masses, and these are not interrelated, although moment and location are interrelated and cannot be taken out of or cannot be taken from each other. But the period of time and the distance are not interrelated, even in the special theory of relativity's approach.
Well, listen, I want to thank you for, I think we're going to stop the recording, but I want to thank you once again and inviting so many people along. It's very great to have all your colleagues. In fact, we've added a couple new people. We've added Garrett and Paul de Haas to the database, so we're finding new people. I think, again, I congratulate you on two very important points, in my opinion, that I can see in your work. And again, this is my opinion, but your work with general relativity and showing that wrong with experiments, I'm really going to read into that a lot more. I think that's just phenomenal work. I also want to congratulate you on your engineering approach to physics. I think one of the biggest problems is the theoretical side starts to take over, and people forget that experiment and engineering. In fact, in my movie, one of the big points I'm going to make is that, in fact, the Stanford Linear Accelerator scientist who is in the mainstream, I told him, I said, "So you're a theoretical physicist?" And he jumped on me. He said, "There should never be anything theoretical about physics." And so I want to applaud you on that attitude. I want to also congratulate you on your fighting for these ideas, because I think you've had struggles like anybody else, but I will tell you, your ideas are welcome in our group. We have people who are of like minds, and that's what the idea here, to hear you again and have you speak again and continue your work. And I also would invite you to join in some of our other speakers, because I think what's really important to meet, as you know, we're always coming against this brick wall of the mainstream of trying to publish simple conclusion that the mainstream will never change about those things. So I think we are now finally gathering, finding ourselves. Let's all work together. Let's find our commonalities. Let's also learn from each other and adjust our own ideas according to a lot of other people's work. I know a lot of my ideas have changed just by listening to people like yourself. A year ago, if you had told me general relativity was completely wrong in its predictions, I would have laughed. But now I've seen numbers of people, and so I will say I myself have changed my ideas, but I think all of us have to do that. So I want to thank you, and if you want to make any concluding remarks before we end, you can do so. Then we'll stop.
Okay, thank you so much.
That will be available to everybody. So if you have any concluding remarts,
I
would
will
love to have those before we stop our recording.
Thank you so much. I will indeed thank you. I will thank to you, first of all, for having allowed me to meet yourself across this bridging, and so many wonderful people. Thank you very much for your comments. I like to thank to my colleagues, and I like to thank to all these beautiful people who have listened to my talk as far as I can see, with no bias at all, with sageness, and I like to thank them for having applauded me so heartfully. I have had my gifts for many years, I would say. So again, thank you so very much, and bye bye to all. Goodbye.